All right, what's up, my peoples? And this is structure-free learning again. And check this out. We're gonna go back to our conjugate beam methods. And if you can agree that in the conjugate beam method for structural analysis and beam deflections, that the uh, the slope in the real beam is equal to the shear in the conjugate beam, and that the deflection in the real beam is equal to the moment in the conjugate beam, then really all that's left is statics and the hard part. And the hard part is drawing the conjugate beam. And in order to draw the conjugate beam, you just, really the thing to do is look at the tables in your textbook and utilize those, because all it is about converting the boundary conditions to the proper boundary conditions or supports in the conjugate beam. So taking the boundary conditions in the real beam and converting it to the conjugate. And the way that, all of that is based on this relationship right here between the conjugate beam and the real beam, or the real beam here, the real deflections and slope versus the conjugate shear and moment. And so and here you'll see this in a lot of tables, right, in textbooks. But here, at a pin, our vertical deflection is 0, and our slope can be anything, right? It can be a number that changes. So what that means is, because this displacement relates directly to moment, in the pin, in the conjugate beam, we have to have a moment equal to 0, and then have a shear here. We have to have a shear. And what that is a pin support in the conjugate beam. So a pin in the real beam at the edge of a beam, an edge pin, if you will, is an edge pin in the conjugate beam. So that was pretty simple. Let me make these. Oh, it's okay if let me do this in purple. So delta equals 0 theta, just to be consistent with this here, m0v right here. Okay, and then the roller, if you look here, again, the deflection is 0. I have a slope here, and so you could just say that the moment here is also 0, and the shear is just a value, right? Because again, you can have any sort of rotation at the roller. And so in this case also, a roller in the real beam is a roller in the conjugate beam. The reason it's not a pin is because you don't want a statically indeterminate conjugate beam, right? Anyway, so there's that right there. And then in a fixed here, you have delta is equal to 0 and theta equals 0 in a real fixed support. And so in a conjugate world, you have to have values for moment. These have to be 0, and the shear has to be 0, which is a free end. Yay, okay, in the conjugate world. So maybe I should put primes here to indicate conjugate, right? Bam. Okay, and the same thing here, opposite goes true. You can have any displacement, any rotation at a free end, so that means you can have any moment or any shear in the conjugate beam. Yay, so that's a free in the conjugate world, becomes fixed in the other. I have an internal pin here, which means that the deflection here is 0, but I could have a rotation. The rotation can be anything here in this case. And so that is really, I have to have 0 moment and a shear value. Okay, 0 moment and a shear value. Hey, that's a hinge, right? And the same thing here, I have delta equals 0, and theta could be any number. Oops, I can rotate still for internal roller. So theta could be any number. And so here again, I need the moment to be 0 to correspond with my 0 deflection, and my shear could be any number, just like a hinge. And so again, this internal pin and internal roller both translate into a hinge in the conjugate beam. And then here a hinge in the real world, where you can have both deflection and rotation. Oh, deflection and rotation. I said it in the opposite way I wrote it. Oh no. Okay, but who cares, right? Doesn't matter. Here I can have a moment, and this might look a little confusing, right? Because some of you might be used to drawing a 0 moment at the internal roller, which is not true. Only if the roller is at the end, okay, at the end of the beam, beginning or end of a beam, but not intermediate. So here I can have a moment, bam, and a shear here. Okay, and the moment would just go across. I can have a shear because this thing can just rotate, so that'll be from the reaction. All right, hopefully that helps. And let's do a couple examples just to see what that looks like for us in terms of taking a real beam into a conjugate beam. So I got a couple examples set up here. So I've got this real beam here, and I want to take this into my conjugate beam. So these will be my conjugates. Or my bizarro beams, conjugate beam right here. And so here I've got a pin in the real beam, which is really just a pin in the in the conjugate beam. Sorry. Okay, so a pin in the real beam goes to my pin in the conjugate beam. I have an intermediate roller at L1, so that in the conjugate world is a hinge. And then here I have a free end here, which in the conjugate beam is a fixed end. And this is what my conjugate beam would look like. None of my lengths change. This is still L1, and this is still L2 right here. Yeah, there's my conjugate beam. And then you would take the curvature diagram and apply that as a loading on the conjugate beam. And then look, this is this still statically determinate? Oh, this one is not, but we can probably analyze it like statically determinate as long as there's no lateral loads. Let's see, let's make sure we did everything right. Yeah, that looks pretty good. Internal pin, internal, yep, to a hinge. Yeah, that's what I'm talking about. Oh, internal roller to a hinge. Yeah, that's what I'm talking about, right? Okay, and then here I have a fixed beam. In the real world, I have a fixed support at the beginning of the member, I guess, and then a hinge at L1, and then a roller at L2. And so in my conjugate beam here, I've got bam, and that hinge becomes an internal roller. Boom, roller, and here the roller becomes a roller. Bam, and this looks unstable, right, if I have a horizontal load, but anyway, it'll work in terms of the conjugate beam, but here it'll work as long as the loading is vertical. But this is technically an unstable structure. But again, here this is how it gets interpreted in the conjugate beam, and all you've got to do is use statics with the curvature as a loading to solve for the deflections. All right, so hopefully that was helpful and you've enjoyed it. And we'll do some more example problems, I guess. Yeah, why not? See ya.